Morning, everyone. So today we're going to start into a new section here. It's actually a very tiny section. Now that we've introduced a lot of the organic families and different functional groups here, we're going to see some experimental techniques and some instruments we can actually use. Each of the instruments are going to use a different energy form. Some uses X-rays, some uses IR radiation. They're all going to give us hints to what the molecule looks like. And like an investigator, we're going to go in, collect up all these evidences, and try to figure out what we've actually created. If you do this in detail here, you can actually calculate sort of the amounts of different functional groups present as well. But I just wanted to introduce some of these spectroscopic techniques to you here. So this package here you can find under the resources column here, and we'll just go from there. So starting off with our spectroscopic techniques here, in terms of our data booklet here, we're going to look at three primary energy modes that you're going to put in. One is infrared radiation, so IR radiation. Infrared radiation, just in general here, infrared radiation tells us something about the bonds, so it's going to tell you what bonds are present. NMR data, this is actually looking at actually radio frequencies, really low energy waves, and this one here will tell me something about a hydrogen environment. More on that later on. Basically, this gives me hints where how the hydrogens actually look like in my structure. And then we're going to do today more so these mass spectral fragments here. This one I'm going to bombard a fragment here. I'm going to be able to find things like molar mass. I'm going to be able to find different groupings from the MS here. And on our data booklet, section 28, you actually have some examples of them. Okay, so just a brief introduction as we go through here. Why are we interested in doing spectroscopic techniques here? Sometimes you're just interested in doing a very qualitative analysis, okay? So qualitative, I don't really care about the amount. I just want to detect for presence. Is this thing here, let's say if I was Olympic Games and I want to figure out, okay, did this athlete take some forbidden species here? As long as that's present, that's just qualitative, I don't relatively care about the amount. Next one here is quantitative analysis here. For quantitative, we're talking about, well, quantity or numbers. So this one here is not just is it present, but I want to know it's present in what amount. So for example, if a cop pulls a driver over and they want to say, well, have they been drinking? There's sort of a legal limit. Well, it's not just whether they have alcohol in the system, but it's also, well, is it beyond the limit that they set? We are going to sort of take down the evidences that we get from all these different modes to try to do some structural analysis here to try to actually figure out not just what chemical we have, sort of how many carbons, how many hydrogens, but also the arrangement. So I would be interested in what sort of functional groups, right? Because that's going to tell me some sort of behaviors there, maybe what which isomer that I have. We found that especially when things start getting larger, we can have structural isomers, I can have stereoisomers, RS, EZ, all those things. Okay. So just before we get into our main technique for today, mass spectrometry, we're going to take a look at degree of unsaturation. I'm just going to say this is sort of hint number one. It's also called an index of hydrogen deficiency. This one by definition is how many H2 molecules would I theoretically need to use to convert the current molecule into the saturated non-cyclic molecule here. Okay, so I'm just going to give you an example here. Let's say I have the molecule, I have 4 carbons in a row here, and I have 1 double bond, 1 triple bond there. Okay, so definitely because I have multiple bonds here tell me we're actually unsaturated. Okay, so multiple bonds, this one here is unsaturated. Right? Unsaturated fats have multiple bonds. Okay, so this index of hydrogen deficiency, or how many degrees of unsaturation do I have, it's theoretically how much H2 I can add to the system to convert it back into the alkane, just straight across, no rings. So what would happen here is to convert this C2H, what would be C2H4, back into a single bond, I would need to add 1 H2 here, so that's 1 degree of unsaturation. I would need to add 1 H2 here to get rid of the triple bond and make it a double bond. I'd add another H2 here and then actually make it a single bond here, and therefore I have 1, 2, 3 degrees of unsaturation, or the index of hydrogen deficiency is actually 3. This one here gives us a really simple hint here of, well, how many possible rings or how many multiple bonds does something have based on the number of double unsaturation that it has. Rings similarly here. Let's take our butane again. I have 4 carbons like this, and I want to actually form a ring. Every time I form a ring, I end up losing 2 hydrogens, right? Because what would end up happening here is I start off with C4H10, right? I would need to ditch the 2 on the ends here and end up joining these 2 carbons here, and that ends up forming the compound C4H8. I've actually lost 2 hydrogens. So every time I form a ring, for each ring formed, I also have lost 1 degree. So the index is also 1 there. So if you want to make a conclusion for yourself here, we lose 2 H's per multiple bond. So when single bond goes to double, when double goes to triple, another 2 hydrogens, or if I have a ring. So if you already know this degree of unsaturation, that hints to the molecule. Does it have multiple bonds here? Does it have rings? Okay. There is actually a generic formula. If you want to memorize this, you can. I generally find it's easy enough. Given the compound, you could just sketch it out. So I'm just saying CH. These are the very common elements here. I'm using lowercase subscripts here. These ones here actually tell you, well, how many carbons, how many hydrogens, whatever. And there is actually a formula. If you wanted to memorize, yes, this formula would also give you the answer. So for example, we can take an aromatic. Let's take benzene, C6H6, right? So I have this structure. What I would do is I wouldn't use the formula. I would just go, okay, well, what do I have? I have the equivalent of 1, 2, 3 double bonds, and I have 1 ring. I already knew it was 4 degrees of unsaturation. If you want to use the formula, let's just check if it works here. There's a static 0.5 out here times 2 times the carbon number. The carbon number here is 6. So 2 times 6 plus a static 2 minus off the hydrogens. So I have 6 of those minus off X. X is actually going to be a halogen group, so I don't have any halogens right now. And then if I have any N groups, again, I don't have any nitrogen, so minus 0 plus 0. Okay. So let's work through the math there. 2 times 6 is 12, plus 2 is 14, minus 6 is 8, times 0.5 is 4. Okay. So you can use the formula, but you would need to memorize it. I find it's generally easy enough just to sketch it out. Okay. So I'm going to do this first one with you here. Let's try C4H8O2. Okay. First thing I would do is I would focus on the number of carbons, right? If this were fully saturated, my general formula of an alkane should be CnH2n plus 2. So if I had a C4, I would have expected 2 times 4 plus 2. I would have expected this part here to be 10. And what is it now? It is actually an 8. Okay? So that tells me, well, I have lost 2 hydrogens. That's 1 degree of unsaturation. The question here is, what about the oxygens? Does that actually change things? Long story short is no. Let's just have a look. Say I have 4 carbons, right? If I have 1 degree of unsaturation, instead of the 10, I now have 8. What are my possibilities? Well, I could have the equivalent of a double bond. Let's just count how many that I have left, right? Every carbon has the equivalent of 4 bonds. I should be able to see where all 4 of carbons valence electrons have ended up. And you'll notice here I end up getting 1, 2, 3, 4, 5, 6, 7, 8. Perfect. I made 1 multiple bond, I got 8. But now I actually need to have 2 oxygens. Why did I say oxygens here don't end up mattering? Well, let's assume here we actually had hydrogen, hydrogen. What if instead of these are just plain old hydrogen, what if I made oxygens on the end there? Well, if I put the oxygens there, that doesn't change the number of hydrogens. That also doesn't change the deficiency. It doesn't end up removing any hydrogens or anything like that. That just sort of makes it an alcohol functionality. Okay, so that is a possible isomer. Right? We have 1 degree of unsaturation, and that hints either you have 1 double bond or you have 1 ring. So let's see what could happen. If I have 4 carbons and a ring, that would already be C4H8. That's what we want. And again, what we need is we need oxygen groups here. Again, we're stuck with doing sort of OH like that. Okay. So those are 2 possible isomers. Definitely, if I look like one or the other, like I'm totally different functionality. Okay. Could I be a carbonyl functionality? Could I be a, let's say I had 4 carbons, right? Well, I wanted a double bond. Could I potentially be a double bond oxygen? We'll just try it. So I have hydrogen, 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 okay? So we have 1, 2, 3, 4, 5, 6, 7, 8. Perfect. We're still good. The oxygens here didn't really matter. I have the equivalent of 1 double bond. I could be an alkene. I could be a ring. I could even be a carbonyl group here. Evidently, I have 1 more oxygen, so I would probably have another alcohol group there. I could be an ether as well. The oxygen might even come mid-chain. So if you didn't want a OH group like that, you could have put an O group in the middle, right? That's why in the formula here, you actually see that the O group actually doesn't end up changing anything. Okay. So either with the formula. You'll probably need the formula for these compounds unless you look up the structures and actually draw it out for yourself. You can find the index of hydrogen deficiency. That is a double bond equivalent. Okay, so that's one hint we can use, no problem. As we start looking at different chemical instruments here to actually analyze molecules, different types of spectroscopy, different types of this sort of experimentation, in general, we're trying to send in radiation of different energies, and we're seeing how the matter actually interacts with this radiation. Fortunately for us here, the whole EM spectrum here is actually a much wider range. We've been doing a lot of sort of visible and UV spectroscopy here. When we did, we'll see this on the next page as well, when we did things like absorption and emission studies. So like, oh, how much energy do I need for an electron to promote itself, to jump from shell to shell? That gave you information about electrons, but that was relatively a big size here. In this case here, we're actually going to use IR radiation. IR is going to tell me something about the stretchiness of bonds. I'm going to use lower microwaves and radio waves for NMR spectroscopy later on here. These ones here, which are much less energetic, will also interact with matter, maybe not so much with the electrons, but also with something else in the molecule, giving me more hints, more evidence for the molecule. So we're basically going to piece together all this evidence here, what I know about percent composition, things like molar mass, empirical formula, those notions there. That would probably give you the number of C's and H's and O's or N's in the compound, but we still need to know, well, how are those actually being arranged? Mass spectrometry we're going to look at today. Proton NMR, there's actually other types of NMR as well. Nuclear magnetic resonance spectroscopy, this uses radio waves, really low energy. IR, like I said, is looking at the different bond strands. We can even use more energetic forms. So beyond the UV region, we can use the X-rays for crystallography. That one we don't need to know in detail, but that one just helps us find bond angles, bond lengths. Right. And it's not one experiment technique is better than the other. It's hopefully you can collect up all these evidences, and hopefully it'll support you in sort of which molecule it actually is. So here's just a rough note here of the EM spectrum. We're going to go from this side here, starting from the low energy. We're actually increasing energy as we get to the table on the other side here. So increasing energy. So relatively low energies here. We have our Planck equation, E is equal to HF. So we have a corresponding frequency. Even though this is relatively low energy, the frequency is still ridiculously high because the speed of light is actually really, really fast. We have the universal wave equation here, C is equal to F lambda. All light travels at the speed of light. So all light travels at this constant 3.0 times 10 to the 8 meter per second. That assumes in vacuum, especially in physics when it enters different media here, it could slow down, that can cause bending and whatnot. And they're just giving you just a feel of how can we utilize each form of radiation. So this one here, this process here will be for NMR. We'll see this towards the end of this section. It can cause a nuclei to actually reverse spin. So what's happening here is our nuclei is made out of a bunch of protons. We're going to look at proton NMR, so just hydrogen NMR. Protons, like electrons, have this property of spin. They can either be spin up or spin down. Radio waves are enough to actually cause the proton to actually flip from maybe a spin up state to a spin down state. So if I can cause that to happen, we're going to use NMR. This is going to tell me something about the different chemical environments. That's actually going to give me most information about the functionality. Keep going here about microwaves and infrared. Well, why do we put foods in microwaves? Microwaves are actually the perfect right amount of energy to cause water molecules in my food here. These bonds here are never like static. They're never like always a constant length. They're more like springs. And they're constantly bouncing back and forth. Their bond lengths are getting shorter, longer. Bond angles are getting squeezed tighter or farther away. They're dancing around a little bit here. Microwaves, as you send them in, they cause more of these vibrational modes here. We see that better with the infrared radiation. The infrared, the IR spectroscopy, will tell me how bonds actually stretch and vibrate. And this one will actually give me information about which functional group is present, how things are actually attached. We're not going to touch too much on visible and ultraviolet. We already talked about that in previous. We did Rydberg equation. We did electron transitions like n equals 1, 2, 3. The energy shells get closer together. That was typically in the visible region. So if you remember for your transition metals here, if I send in exactly the right amount of energy, maybe for transition metals, I should show you the splitting again. So I have 5 d orbitals, and then when ligands are present, we get 3 lower and 2 higher like this. If I send in energy that corresponds to the visible region, that's going to absorb up one color as long as I have room up here. And then we're going to, instead of having a Roy-G Biv, instead of everything constructively interfering, we're going to end up having just one color, the complement being released. So not only did this actually help me tell you absorption spectra, emission spectra here, it also helped me figure out why transition metal ions are colored. X-ray is going to end up giving you a method called X-ray crystallography here, and this way, just roughly speaking, it basically gives you a shadow of the picture, and there you can measure, oh, from this center to this center, here's how far the bond is, and here's the bond angle between them. Gamma rays here, it also interacts with matter, but super high energy here, no sort of common use of it at the moment. Okay, so for the rest of this lesson here, I want to just emphasize on the sort of first main technique. So we had index of hydrogen deficiency. We already knew, do I have the equivalent of a double bond or do equivalent of a ring? Second rule here is a mass spectrometer. In the new revised curriculum here, they say you don't need to know all the steps of mass spectrometry here, but they are going to go through it in a little bit more detail anyway, so I may as well just go over it with you. I've given you a little schematic of a mass spectrometer over here. This actually takes place in 5 steps. First step here occurs. First step is a vaporization step. So step 1, vaporization. Basically what ends up happening is we end up atomizing the sample. We end up, if the molecule here was a diatomic, if it was like, let's say Cl and Cl, it already is gas good, but I want to be studying sort of the different fragments, the different parts of it. Earlier in chapter 2, we were interested in isotopes. Maybe this is a 35 form and a 37 form. I don't want that to actually go through the device together. I want to actually break it up. So I atomize it to become, maybe these are 35 and maybe these ones here are 37. These ones here will be radicals. When you atomize something, back in chapter 5, we're actually forming gases of them. So I'm going to do a gas. Gases are sort of widely separated here. They can be sent through this device here really, really easily. Second step here is kind of crazy. This is the one that we're going to focus on mainly. Second step is actually to bombard. We're going to actually do a process called ionization. So ionization, yes, ionization in general means make it charged. In this case here, we're using electron bombardment. I'm actually sending in electrons, engineering almost some car crashes here. These really fast moving electrons are going to hit my chlorine radicals here, and hopefully as these electrons bounce off, they're going to actually dislodge electrons that previously were on there. Okay? So I have some free source of electrons here. I'm going to collide it with the chlorine. As this chlorine here ends up losing an electron, that's an oxidation process. This in here actually becomes charged. So we're actually going to try to form X plus ions. Right. It could very well have been negative ions as well, but bombardment is easy enough just to form positive. Okay. The reason why we want them to be positive is we're going to focus more on that ionization step in a second here. We're going to send it through the third part. The third part is actually an acceleration. We're actually going to set up an electric field. Now that we have suddenly all these positive charges, if I have one plate set as positive, the other plate a little bit negative voltage of there, the positive ions will actually have an acceleration that will actually be sped in this direction. So for acceleration, we're actually using an E field to move our cations. And I actually want to direct them so they actually go through the rest of the device. For simplicity, let's imagine there's just one hole in the plate. So if my cation was perfectly aligned with that hole there, not only would they have a tug and actually a speed towards the negative plate here, they're actually going to be sent through the rest of the device. The fourth step here is probably the most important. The fourth one actually uses a magnet, uses a magnetic field here. We start from no magnetic field, and we slowly ramp up the magnetic field. So the fourth step here, we're going to call that a deflection stage. We're actually using a magnetic field. Magnetic field, for some reason, they use B for it. Okay, so B field to deflect charges, to bend the charges. And essentially what's happening here is before any magnetic field was on, I had all this velocity here going out of the plate here. I'm actually hitting the other side of the container. I'm never actually going to make it down to the detector. You notice there's a nice 90 degree here. So what ends up happening here is as I slowly ramp up the magnetic field, This magnetic field here is going to direct charged particles sort of perpendicular to the rest of the device. At first, the lighter particles are going to experience more of a pull. They're going to be able to make it down this tunnel here. If I'm too heavy, nope, I'm out of luck. I still collide with the far side. And then all I'm going to do at the end, this is step number 5, I'm going to have someone sitting at the end as a detector. We're actually just going to count how many end up making it. So a detector, we're going to actually end up forming a mass spectrum. We're going to actually figure out, relatively speaking, how many particles actually were deflected based on a mass per charge ratio. So there's a little bit more to this. Nicely here, because we are a cation, we're +1. If I go mass divided by +1, well, that's just basically the mass. So imagine at first we had no magnetic field. None of the particles actually make it. We slowly ramp up the magnetic field. We slowly make it so that some of the particles start getting deflected. We spend an equal amount of time at each of these settings here. As these light particles here end up making it, I count how many make it at that setting. Then I change the setting again here. Then what would happen is those light particles will end up hitting the close side of the detector, right? Those don't end up making it. And the ones that were slightly heavier than it here, the ones that previously didn't quite bend enough, now those ones there have a chance to actually bend and hit the detector. So we actually just do this nice scan here, and we get many different hits. This one actually tells us the different isotopes that we have, and also the heights, the areas under the curves actually tell us the abundance. So that's actually how it looks here. Again, there's a lot of detail in there that you don't really need to know, but they're going to just give you these mass spectrum. They're basically giving you this stage here, and we're going to focus more so on the ionization in this section. So when we start doing mass spectrometry, when we stick it through a mass spectrometer here, it's used to find molar mass. It's used to tell you sort of the molar weight of the thing present. I already told you it can be used for abundance of different isotopes back in chapter 2. Remember how we had that formula, weighted average from the periodic table, where all these percent mass plus percent mass, right, plus any number of them, right? The mass is skewed towards the one that's most common. We're going to focus mainly on the step number 2. During our ionization step, during our second phase here, we engineer high energetic collisions here between the atomized species, and we're trying to actually dislodge electrons on them. So I send in an electron. It's actually used just to hit the X. This one here ends up bouncing off. I'm hoping that this X here will actually dislodge its own electron. So therefore, at the end, I have an X with a positive charge. If I do this a little bit too frequently, too energetically, this could become X plus 2, X plus 3. That can interfere with things later on. But definitely, we have 2 electrons left over, one from the one that I bombarded and the other one from what is lost. The MS here gives me what's referred to as a fragmentation pattern. It gives you some information, not just about the molar mass, it tells you something about the structure. So here are some things you can read. So let's just do as an example for ethanol here. First thing we're going to do here is we know it's ethanol. Let's see what this one here would actually give us. You're going to actually look at the very top fragment here, and you're going to assume that this one here was, you had your bombardment, the electron ending up hitting this ethanol molecule here, and essentially what ended up happening is something on this molecule has actually lost an electron. I don't necessarily know who, but this one here ends up forming this ethanol, but it has a positive charge somewhere. Could be there, could be there, could be there. It doesn't really matter. So I'm going to assume that the largest fragment is going to be the parent ion. So my molar mass is actually given by the highest one. That's going to pretend like the only thing that's happened is I've lost an electron, and the electron practically has no mass there. Okay. Whenever I do this fragmentation, one thing always takes the positive, the other thing is neutral, right? Because there has to be a conservation of charge. So in total, I've lost an electron. In total, I need to have 1 positive charge overall. What's going to end up happening here is this electron bombardment actually occurs so violently, not just the parent ion. Notice I don't have a lot of parent ion here. It stays intact here with having lost that electron. What can happen here is this electron can actually fragment the molecule, can actually crack this molecule into many different types. So very often here, you're going to see from the parent molecule, you're going to have 1 smaller than it. Well, what has a molar mass of 1? If I end up losing an H+, so I basically fragment it, so the H+ leaves, and I'm left with this radical here temporarily here, then I have this one. Now I have a mass of 45. So all these ones here with a mass of 45 have indicated my parent has actually lost the hydrogen. Okay. What if I lost a mass of 15? Well, 15 here on your data booklet, you're going to be told 15 is characteristic for actually a methyl group. Again, we start off with a parent ion. It's 46. This one here is the positive, so it's going to be sent through the device. As I crack this, as I break off something, let's say I end up breaking off the CH3 grouping. So if this CH3 group leaves and that group here has the positive, this is actually going to be sensed at the 15 spot. Right, so these ones here are because of CH3 positive. Right, you don't need to memorize that. That's going to be given to you. So 15, CH3 positive. The other part here, well, what's 46 minus 15 here is going to be 31. The other part here, this one, because it's not charged, so it's undetected. Remember, it was actually the electric field that was actually accelerating these charges here. It's only positive things that actually will sense this one. If I have something that's not charged, they might naturally float through the device, but they're not going to necessarily hit the other side. So why is it that I'm actually getting a lot of 31? So when I crack it, when I actually break off this methyl, either this CH3 takes on the positive, that ends up showing me the 15 peak, or it could crack the other way here, where the CH3 leaves, but the positive is actually on the other portion. My other portion here, 46 minus the 15, is 31 peak. If this one here is 31 and is positive, this peak here is actually shown on the 31. And so in fact, there's actually a lot of it. So this is super important here. It's only when you crack it, only one thing keeps a positive charge. Only the charge fragment is detected. Okay. So there's two ways of starting reading this mass spectra here. On the data booklet, you're given a bunch of common groupings with their masses. The parent ion is always going to be the biggest one. You can look for the numbers directly on the table. Oh yes, this is a CH3 grouping. If that has a charge, yes, you have detected that. Or you can look at the difference. What if 46 has lost my CH3 grouping? If I end up losing my CH3, 46 minus 15 gives you a 31. This one here could be the remnant, could be the other part. If the other part, this CH2OH part, takes on the positive, I can end up seeing that as well. So look at the grouping directly and look at the difference from the parent ion. So they demonstrate this for you here. If I lost an H, notice again it's the positive fragment. The peaks I see at 45 are because of this grouping here. If I end up losing a methyl group here, where the CH2 has the positive, that ends up sensing as a 31. There's another grouping here. What if I lose the OH group? The OH has a molar mass of 16 plus 1, so 17. Well, I don't have any 17 peak. Again, you can think of this as, what if I did 46 minus 17? 46 minus 17, if I lost hydroxyl with the 17 mass, this would end up giving you a peak at 29. You're not going to find maybe the 29 actually listed on the data booklet, but that was because you've lost something that you know to be 17. Okay. Anytime you're just losing one, it's just going to be hydrogen. So with that in mind here, let's see if we can identify some of these. Obviously, they would have simplified things a lot. Okay. In general, it's a little bit hard to identify which every single peak corresponds to, but you should be able to give me a feel of what's present. So identify the following peaks of propane 1O. So I have propane 1O. I would just draw it out first. Right, so it's an alcohol functionality here. The biggest one should be my molar mass. So propane 1O here has C3. It has H, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to put C3H7 and the OH that differentiates as an alcohol grouping. If you look at the molar mass, they already told me it's propane 1O, so you can do the molar mass. 3 times 12 is 36, plus 8 is going to be 44, plus 16, 60. Good. So my molar mass here is 60. What can explain the fragment at 59? Well, if I was basically this, that electron bombardment here is going to start fragmenting. It's going to start making larger molecules, smaller molecules. If this electron bombardment actually dislodges a hydrogen, and the remaining grouping here is actually positive, this part here would be my CH3, CH2, maybe I should, sure, okay, CH3, CH2, CH2O, maybe I have that group left, and that's sort of having lost an H group. So I was a 60, if I lost one, I'm hitting at 59, the remaining part of it is 59. It could have been that hydrogen, could have been another hydrogen, but that part there has to be a positive there. Okay? How about the 42 here? So 42, I see a few I have a 42 and a 43 as well. You can check the data booklet here. On the data booklet, it's actually given like this, okay? So it's given some common grouping here that's lost, corresponding to the masses. Oh no, I don't actually have a 42 actually listed. Remember, don't just look at this one here on the table. You can look at the difference. Well, 60 to 42 is actually a loss of 18. Is there a group that would have lost 18? 18 could be the example of a water grouping. Well, if I somehow lose maybe an OH and I lose this part here, right, that part there would then give you your molecule, okay? So again, it's not easy to identify in general what all the exact peaks are, but maybe potentially I lost the equivalent of a water. Maybe I lost the water, and then I have what's left over. I'm going to get a whole bunch of different radicals, crazy compounds here. Doesn't necessarily have to be this, no, but based on what I just drew there, if I have this one, just indicate to yourself it has to be the positive charge. So again, one important note is you can look for the number directly. If I see a group at 29, right? So if there was a peak at 29 here, I can see, okay, maybe 29 means I have this fragment left. Or you can do the difference. You can go from 60 to 29. I would have lost 31. If that takes on the positive, the 31 is actually losing this, leaving you the rest of it as positive. So if I end up fragmenting it over here, and I just had this part here positive, that part would be the peak at 29 having lost at 31. Yeah. So one more example for you here. A molecule with the empirical formula CH2O has this simplified mass spectrum. Let's deduce the molecular formula. Again, easiest is the parent ion. So this just assumes that you've just dislodged an electron here. The parent ion here has a molar mass of 60. Your empirical formula, your simplified ratio, 12 plus 2 is 14, plus 16 is 30. How many empirical units would I need to end up making that? Well, my molecular formula will probably be twice this one. So C2H4O2. So I already know how many there are. Remember, in organic, right, this could be many different functionalities. This could be many different isomers. They're just saying give one possible structure that has this fragment here. So let's think degrees of unsaturation. C2 was supposed to have 6 H's, and yet now it has 2. So the index of hydrogen deficiency is actually 1. That's indicative either you have one double bond or you've ended up forming a ring. Other things I would look at here is, I know I have a molar mass of 60. Let's look for these numbers by themselves on the table. I might have a methyl group, so that's going to be CH3 positive, right? I might have having lost a methyl group, so I have whatever my parent ion. If I lost the CH3, if I lost something that's 15, 60 minus 15 is 45. Having lost a methyl group here, 45 is a Cu group, COOH. So maybe this one here is COH. Again, the emphasis is it has to be positive or else it doesn't get sensed. And then I have a 43 as well. I don't have an exact match for there, but again, you can look at the difference here. What about 60 down to 43? That change is actually a drop by 17. Maybe I've lost an OH group. Okay. So what molecule can you think about that has the equivalent of one double bond here? Maybe it has a methyl group, maybe it has a carboxyl group, an alcohol grouping. Well, that might just very well be a carboxylic acid. So let's take ethanoic acid. They didn't tell me what it was. Let's try it out. Let's see if it sort of matches all the evidences that we had from before. So in terms of our formula, we have 2 carbons, 4 H's, 2 oxygens. Good. We have the equivalent of a double bond. Again, it didn't have to be an alkene. We are 1 degree of unsaturation. If I take this molecule here, the electron bombardment here happens. If I dislodge just an electron here, that would give me my molar ion peak, parent ion peak as 60. If I end up breaking off this CH3, if this CH3 ends up taking the positive and I end up getting a Cu group like this, I get to sense this one here as the 15 peak. Or if the cracking happens the opposite way here, where I have my CH3 actually neutral and the COH actually being positive, this one here would be my 45 peak. I have peaks at 15 and 45, that's good. And then they also give me one fragment. I didn't have a 43 on the table, but we said, what if I lost a 17? I lost the OH group. Maybe my electron bombardment has actually dislodged this one. Who takes on the positive for me to actually have a mass of 43? I would have had to lost an OH grouping. This one here breaks out to become our CH3, C110, and then our OH like this. The OH would have given you a 17 peak. I don't see a 17 peak. I only see the 60 minus the 17 peak, so that means this side here takes on the positive. Yes, that's a radical, and this one here would probably be your 43 peak. Okay. That is one possible isomer, and based on the mass spectrum, it supports it's possibly this structure here. Okay. So I'll leave it off there, and we'll pick it up from there tomorrow. Thanks, guys.